Anyway, what I'm going to tell you about is, or try to tell you about is the work we've done on the problem of how glasses age. There might be some lessons for this for aging in biological systems, although it's not clear to me, especially since I've been listening to most of the conference earlier. I would say one aspect that may be relevant is certainly many of the biological systems that we look at the larger length scales actually are glassy. The cytoskeleton has been shown to have glassy characteristics. Probably the chromosome has glassy characteristics under some conditions in terms of its mechanical properties. And certainly assemblies of cells probably have glassy aspects. Because they're large systems, this is basically the main reason why the glass physics turns out to be relevant. The other perhaps meta lesson is this, that it's very hard to study time-scale processes, and the problem of how glasses work is actually intrinsically a long time-scale process. It's the question of how a material that on the atomic scale is moving on a picosecond time scale appears to us not to be moving at all, or perhaps to be moving extremely slowly. So in fact, the aging of glasses is their very slow dynamics, even when they appear superficially not to change at all. Why does anyone care about that? Well, for engineering purposes, it's very important, even a small change of the dimensions of a glassy piece of material in a mechanical object. So in fact, the studying of the aging of glassy materials goes back to the study of silk fibers by Gauss in the 18th century. So, and for practical problems. So there's a great deal of practical work on it. However, because of the long time scale, it's very hard to study the problem in a purely experimental way. It's really only when I would say you compare experiment and theory that you have a chance to learn something. Now, I heard a lot about the importance of thermodynamics from the earlier speakers, and clearly we're on the same wavelength to a certain extent here. Glasses are not systems that are obeying exactly the simple thermodynamic paradigms that you learned in school, although they do, of course, obey the second law of thermodynamics. But they come close to following the paradigms of systems that are not changing at all, that are truly at equilibrium. It's this very close to equilibrium apparent aspect of them which is interesting. But of course, the other surprise is that they really are still changing, and that's the problem of aging. Now, when we try to follow the laws of thermodynamics, it's important to remember a little bit what thermodynamics is about. I've heard it sort of bandied about a lot this morning. I'm not sure people think too much about how do you actually use real thermodynamics. This is actually an interesting quote from Feynman in his lectures on general relativity. He says, a physically satisfactory discussion of thermodynamics and statistical mechanics can only be achieved if it is recognized that the problem is to define conditions in a system in which various things happen at very different rates. Only if the rates are distinct is thermodynamics of use. Never in thermodynamics is it true that everything has gone to the final state. It's that some variables have gone to their final state, others are not. And so one of the problems in applying thermodynamics, or coming close to applying thermodynamics, is to understand why or whether you have phenomena that occur at very different rates. And in glasses, we'll see there's a special problem here which makes thermodynamics more difficult to apply than it is to other systems. So one of the questions is, why are systems, why do they have a wide range of timescales? Well, one thing's very familiar to people. One is that there's often conservation laws. The total amount of something doesn't change. It can only be transferred from place to place. This is true of atoms as a whole, in general. It's true of energy in some sense, although there's some issues with that. That's one reason why something doesn't change at all on the global scale. That means that it changes slowly on a large length scale. Another reason something might be slowly varying is that, in fact, it's a balance of two. The situation balances two rather large forces, each one of which would individually move things very fast, but when they are fighting against each other, they cancel out, and you have something that now responds slowly. The more very common situation, the one that turns out to be the key in most of what we're talking about today, is that sometimes events on the molecular scale are very rare. And finally, there's a situation which is also relevant for today, in which there's many possible situations. There's a large configurational entropy of possibilities. Now, actually, each of these mechanisms for having a disparate range of timescales actually is associated with almost an entire branch of physics. So, for example, the fact that we have conservation laws in locality is what gives rise to the theory of hydrodynamics. The fact that we have systems where we can balance two large forces against each other, where they almost come to cancel each other out. This is the origin, fundamentally, of critical phenomena, where things move very slowly. There's a phenomenon called critical slowing down. Essentially, all of chemistry is actually concerned with the problem of rare events. Chemical reactions involve the motions of atoms. Most of the time, the atoms are moving back and forth, doing the same thing. It's only very rarely something interesting happens. Rare events are certainly at the core of how the mechanical properties of glasses change. I'll be exploring that. But rare events also are of interest in these situations that you've been hearing about biologically. Rare epigenetic changes that occur only when a gene switch goes from one state to another. And then finally, the situation, those three fields are fields where we could say there's settled notions of how to proceed theoretically. When we have actually many, many states, when you have a diversity of states, then this is the situation that leads to the phenomena that we call Glassy dynamics. And it's here where aging turns out to be a key point. In these three other areas, you don't really talk about aging. You just talk about the system on a sort of relatively, either on a time scale where the process has happened or not happened, or it's more or less over. In the case of chemical kinetics, we go to equilibrium. Glassy dynamics, one of the problems is that because of the diversity of states, you get two very different phenomena that make it difficult to study a process which is either completely over or just begun. So these two hallmarks are shown here of Glassy dynamics. An ordinary chemical reaction, we're used to thinking of a chemical reaction as slowing down as the temperature goes down. That usually follows this law called the Arrhenius law. So when we look at a chemical reaction, if we rate the log of its rate and we plot it versus 1 over the temperature, we usually get a straight line. What's shown here are the rate of mechanical deformation of or the time scale, rather, of mechanical deformation of a glass, sometimes called the viscosity. It's actually not a glass when we use the word viscosity to describe it. And what you see there is there are a few materials whose mechanical motions respond as if it was a simple chemical reaction. Like when I look at pure silicon dioxide, it obeys an Arrhenius law. But almost all the other substances have these highly curved Arrhenius plots. And this is one of the puzzles of Glassy dynamics. This certainly partly can be traced back to the fact that there's a diversity of local structures in the glass. The other side of that, which is even more obvious, you don't need any theory to see, is that if you look at the response of a supercooled liquid or a glass as it responds to a perturbation, it doesn't follow an exponential law like we've been hearing about. It follows usually a law that suggests that there's a whole range of timescales in it. You typically have a whole range of things, ranging from very fast things to very slow things. There are a distribution, apparently, of different times. And this is why, when you look at the dynamics of a glass, you can't just ascribe one single number to it. You have to talk about the diversity of possible processes going on. Now, glasses almost obey thermodynamics. And what we mean by that is that their thermal properties look like they obey things like what would happen when a material remains near to equilibrium, but but their thermal properties actually display a dependence on their history. So what's plotted here is a very important quantity for several different substances. It's the apparent heat capacity of a glass as a function of temperature. Now, a system in equilibrium really has a definite heat capacity at every temperature, no matter how you got to that temperature. But glasses have the property that their apparent heat capacity is different depending on whether you heat them or whether you cool them, and it depends also on the rate at which you heat or cool them. Nevertheless, you can see, and what's shown here is, for example, in the blue curves, is shown the heat capacity of various substances as you cool them, and at 20 degrees Kelvin per minute. And on the other hand, the red curves show what happens if you heat them after you cooled them up. You can see the two curves don't superimpose on each other, although they have some similarities. And actually the details of how fast you heat and cool doesn't change things a tremendous amount. But one has the feeling, especially because this time constant is getting longer and longer as you do the process slower and slower, that these curves would get closer and closer to equilibrium looking curves at some point, and would be then at some point almost the same on heating and cooling. Now, I've said many times that the reason for this distributed behavior in time constant and the non-Arrhenius behavior is that that there are actually many, many different local structures of materials that are forming glasses. This is one way in which liquids, to a certain extent, this is a way in which these glassy systems are different from at least the caricature of proteins as we see them to crystallography. Individual proteins usually have a modest range of structures in the vicinity of one average structure, and then that is in equilibrium perhaps with unfolded structures. This is what gives rise to the concept of a funnel-like energy landscape. On the other hand, as you get to larger and larger objects, it becomes harder and harder for them to be designed to have these very, very clear structures. And this is one reason why I believe that things like the cytoskeleton, the chromosome, are not nearly, are much more like the liquid glass problem than they are, say, like the protein problem. But one of the things one can do in looking at liquids, if we could simulate them, and so this would then be studying their processes on very, very rapid time scales, is we can sort of look at what do the different energy minima look like, and one finds a wide range of structures if you take a simulation of a liquid and quench it down to very low temperature. There's a procedure done maybe most formally by Frank Stillinger years ago. It was really done by Bernal maybe 20 years even earlier, 20 or 30 years before that. One of the things that turns out to be quite important here is that every time you do this quench, you get a different answer. If you do a very quick quench, as the atoms molecules move around, they descend into different minima. And one of the important things that you see from this is that you have to be there's many such minima. In fact, there's exponentially many such minima. And it's the entropy of those minima which is actually being probed in those thermal experiments. Now, one of the questions you could ask is, if you're in one of these energy minima, how do you move? And the first question even before that is, would that minimum actually be stable against vibrations? And this is where I would say the theory of glasses in its modern form, this so-called theory, random first-order transition theory of glasses, got its start in calculations about 30 years ago. We looked at the problem of how a single aperiodic structure that you would get on quenching a liquid, how would it be stable against local thermal fluctuations? And basically, we used the same kind of theory that one would use for crystallizing a substance. And the only difference is, instead of when you crystallize to form a crystal, there's one particular crystal. Here, instead, there's many, many particular frozen structures that you might look at. Anyway, one of the results of this was the idea that below a certain temperature, actually, a liquid did have one of these so-called energy landscapes, that there are a whole variety of different structures that you can freeze into. And they're distributed in energy, which gives rise to that configurational entropy that we talked about. Now, you might ask, if you were in one of these structures, if it was just marginally stable, you would practically immediately vibrate out of that structure. But suppose you went to a much lower temperature. Then because it's an energy minimum, you have to find some way out of that energy minimum. And one of the reasons why you would have a tendency to escape that minimum is there's so many other possible structures you can go to. There's many more structures that you can go to for a large region than there is for a small region. That's because of this way in which the number of structures varies exponentially with the size of the region. So because of that, you actually get a phenomenon that says that the way an individual minimum moves over to another individual minimum is a lot like the way a crystal, if you were to heat it, would melt internally. It would try to explore all the other minima. It has a trouble exploring a minimum that is locally close to it because that means that you've moved the atoms away from where they nicely fit. And you've gained only a little bit of entropy. But on the other hand, if you move a larger and larger region, you finally get such an entropic advantage to reconfigure that it becomes possible for that region to move. And this is sort of the basic idea of a construction that Dave Thurumala and Ted Kirkpatrick and I introduced years ago called entropic droplets as a way of explaining how the activated motions in glasses would work. Turns out that that theory makes some interesting predictions, one of which is that basically the relaxation time depends on an activation barrier, just like a chemical reaction does. But that activation barrier is inversely related to how much entropy you would have for the different structures. And there's also an additional later result of that theory. It turns out that the coefficient that relates the entropy per unit volume to the barrier should probably be universal from one substance to another substance. And this requires sort of looking more deeply at the theory why that number is universal. But there's a reasonable argument to say that it shouldn't vary by very much. Well, with those two statements, you can now make several very key predictions. One of which is that result from that theory immediately predicts the behavior that I was talking about, that there would be this non-Arrhenius temperature dependence of rates. And that non-Arrhenius temperature dependence is characterized by two parameters. One is the apparent temperature at which the process could no longer occur. That would be the lowest temperature the system could ever remain in equilibrium, no matter how slowly you cooled it. And this says that that temperature where the rate would go to zero is also the temperature where this entropy would vanish. And this theory then predicts that those two temperatures are the same. And this graph that you see here in the insert in the middle shows the comparison of those two temperatures for about 50 substances. And you can see that they are very, very close to each other. That was actually a phenomenon that was known before the theory. So you might say it's a retrodiction. But a prediction of the theory is that the parameter d, which tells you the slope of that curve, is related also to thermodynamics. It's related back to that heat capacity, which has been measured in a lot of things. And that parameter d is also proportional to this a different parameter used by glass physicists called m, which is basically just what is the slope of that non-Arrhenius activation law at the glass transition itself, and it predicts a universal result for that. And it says that if I give you a thermodynamic number, delta Cp, you can again get out a dynamic number, which is the parent activation energy. And here you can see an actual prediction of the model of this type of theory that compares a kinetic thing with a thermodynamic thing. So this sort of picture explains the basic way dynamics occurs in terms of its temperature dependence. It also explains why that relaxation is not exponential. The size of the regions that reconfigure, the sort of nucleation size regions you might have, turn out in this theory to be about the same in all different substances. That's, again, because of the universality of that energy term that I was talking about. Turns out that the regions in a liquid that reconfigure are about 5 molecular diameters in size. Well, if that's true, then it's really a mesoscale object which is reconfiguring. It's not infinitely large, it's not atomic. It means that actually the activation energy to reconfigure a region varies from place to place. And it's that variation of the activation energy from place to place which is what gives rise to the whole range of relaxation times. So you have some regions that happen to be a little bit less stable than they should be. They reconfigure quickly. Regions that happen to be a little more stable than you might have expected them to be, they would, on the other hand, reconfigure more slowly. So this theory actually predicts, again, the variation of this so-called stretching exponent. There was a number called beta in that equation for the non-exponentiality. It predicts it varies with the heat capacity, which in turn varies with this parameter d that I was showing you, the slope of that curve. And the prediction of the theory is this simple line that you see, thin line, and data for about 60 substances are shown there. So this idea that you have many, many states that each one individually acts like a crystal, but there's a range of them, and it's that range that gives rise to the diversity, which is what makes it difficult to cleanly separate the fast processes from the slow, that gives rise to the non-exponentiality. I would say that this is pretty clearly seen from this prediction and its comparison with the experiment. Now finally, I get to the point of the talk, which is the phenomenon of the aging of glasses. Now, as I said, most people's idea is that once a system, a liquid, has cooled down, so it's gotten very slow, it now is so slow it doesn't mechanically move, apparently. That's when we call it, that we say the system is a glass. Well, in fact, the system does continue to change its properties. It does continue to flow, but much more slowly. But you can also do things, because it's so slow, you can also see how that slow process varies with temperature. As we saw, the process that's entropy driven has a very strong and non-Arrhenius temperature dependence. But once the system has become a glass and fallen out of equilibrium, this is now the behavior of the system, which we call the aging of the glass. It still does continue to change. The rate of change, though, is much slower than it was, slower than it was before, but the behavior is now that of an Arrhenius system. Now there seems to be an apparent activation energy. It's much lower than it was before. On the other hand, the rate starts out at the same value that it had in the previous case. Now the engineers had developed a formalism for this, where they said that somehow the system falls out of equilibrium at a glass transition temperature, and part of that activation energy is shared between something that depends on the structure and something that depends on the temperature itself. And this parameter, how much it's shared between one and the other, is called the nonlinearity parameter. It's this parameter x. So a theory of aging should be a theory, at least partly, of how this sort of empirical phenomenological engineering fit works. And that's what I'll show you in a moment. Before I do that, I should say, though, that there's kind of an interesting lesson from this for theorists. If you take that formula, which has is just an empirical formula at this point, you'll see that one of the activation energies in it is really set by how long the system had waited when you cooled it. How long did it take to cool it down to that temperature? And so the properties, instead of writing that things depend on the freezing temperature, TF, we could say instead they depend on the waiting time, T wait. So what you find is, in this kind of formalism, this kind of phenomenology says that the actual equilibration time of a system depends on how long it's already waited in that condition. It does so not linearly, but in a way that has a sort of non-trivial power. It's as if there's kind of multiple clocks, and the multiple clocks depend on how long you've been waiting already. And this idea that there's multiple clocks in glassy systems also occurs in some other theories of glasses. It's something called time reparameterization invariance. And it's actually, I think, possibly a deep idea, but I put a question mark there because we see that although it's the deep idea in the mean field theory of spin glasses, it's a very sort of trivial idea in this picture. Well, it's not only, well, how do we calculate it? Well, the only difference when we're taking the aging of a glass compared to studying those reconfiguration events in the liquid is that the state that you start from is not an equilibrium state. It's cooled down, it's fallen out of equilibrium, so it can no longer cool any further. So its energy is higher than the energy would be if the system was allowed to come to equilibrium if you continue to cool it. So what this means is that in addition to the driving force that was entropy for a region to turn over, there's another part which is energetic. And again, that energy part depends on how much energy is frozen in, which again depends on that heat capacity number that I talked about at the beginning. So this theory actually predicts a value for X and says that it's correlated with the heat capacity. And this is the result of that. The prediction is that the parameter X, the nonlinearity parameter X, is inversely related to the this M parameter, again, like the heat capacity and D, these are correlated with each other. They can be determined thermodynamically alone. There's a very nice simple formula that results when the glass is, you decide on what the glass relaxation time should be. If you take it to be 1 hour, which is a lot of picoseconds, you get the coefficient being 19. And what you see here is the comparison of the nonlinearity parameter of glass as measured and its M value and the prediction from this theory. So this says that a glassy liquid is a mosaic of different structures. Because the structures are different, they're distributed in lifetime. And this tells how much of that is really an energetic bias and how much is a entropic bias. Now, one of the things that's actually interesting about this is I've acted as if, in the case of glasses, the only thing you could do is you could take a glass and cool it. But you can see that once you have time scales that are long enough, you can do all kinds of things. You can cool the glass, heat the glass, cool the glass, do all sorts of things. In fact, a glass blower typically would do all of those. So this other phenomenon of taking a glass after you've made it and then heating it up is called rejuvenating the glass. And you might ask, what kind of structures form when we rejuvenate a glass? And one of the things that happens here that was actually clearest in some experiments originally was that there seems to be some sort of propagating fronts. And again, this theory that I talked about of glasses indeed predicts that. It predicts that a region which is mobile allows regions next to it also to become mobile. Regions that are slow tend to make regions next to that also slow. And those two regions, those two things tell you that mobility is an object that is infective and diffuses from place to place. On the other hand, a region becomes mobilized by these activated events that I've already talked about. These activated events are also how you're able to change the temperature of a local region. And so, so you actually get a kind of coupled problem in which there's a mobility which is generated when the temperature is high, and there's a temperature which is allowed to be changed if the mobility is high. And so the equations that one gets from this actually resemble very much the equations of the combustion of a material. And in rejuvenating a glass, which I won't show you too much about, you actually get phenomena like flame fronts propagating through it, and these have been observed. Now in the aging situation, the thing which is interesting and important is this aspect that, in fact, the mobility isn't the same everywhere. It starts out differently in different places. And someone has to add some fluctuations to that equation. And in fact, that sort of analysis gets rather technical and difficult and has to be done on a computer. So it's work that was actually carried out by a student of mine, Apiwala, who's at Sorosak, where we actually solve these fluctuating combustion equations, again, putting in the inputs from the theory. And one of the things that we get out of that then is if we look at a picture of the glass, we can see how big the regions are that are mobile. We can see how their effective temperature is different in different places, how their mobility is changed. And we can therefore also figure out what this distribution of relaxation times actually was. And one of the predictions early on of the theory that we had that was then confirmed by this sort of numerical calculation is that the distributions of mobility are kind of Gaussian looking in a normal liquid, except they have a long tail to the fast side. There's a lot of fast things, but there aren't very many slow things. The reason is the very slow stuff, if you're in a region that would want to be very slow, your neighbors probably are not going to be slow too, so they reconfigure and free you up and let you explore other possibilities. So that's why you have this asymmetrical lifetime distribution, which was actually shown in this paper I referred to very early on by Laura Kaufman, where she actually also measures this distribution of lifetimes in single molecule experiments. One of the other predictions from this is that in the glassy material, after it's come out of equilibrium, because the structure is no longer changing, actually things do not get stretched as much as you cool as they would if the system remained in equilibrium. This is, again, one of the predictions of the theory. It's a prediction that's been also confirmed in experiments. There was also a very interesting prediction in a sort of semi-quantitative version of the theory of aging was done with Vasilchenko now about 10 years ago. One of the things that we predicted and mentioned just in one of the footnotes practically was that in a glass which has been quenched, and then if you let it wait for a while, then some of the regions have actually fully equilibrated and therefore they're now very slow. Whereas the other regions, which have not yet equilibrated, they're actually relatively fast. So we predicted actually 10 years ago that there would be a bimodal distribution of relaxation times. This would really screw up that idea of time translation, time reparameterization invariance that I talked about. So that's why I put a question mark there. And actually just last year or 2 years ago now, in Physro of Letters, there was an experimental paper that showed exactly these two mechanisms. Unfortunately, the experimentalists didn't realize that it had already been predicted. And this, on the other hand, is sort of a comparison of their results and the results of those simulations. So I think the point I want to make is that, aging, at least in these kind of systems, is very hard to study, but by pure experiments. But theory really can help us a lot in understanding it. Theory has been very successful. I think that this means that looking at aging of biological glasses is certainly something one can do real theoretical work on. On the other hand, it's also clear that the experiments, because of the long time scale, are typically going to be hard, and if you don't want to believe in theory, you're always welcome to just keep curve fitting. Anyway, the glass problem has been understood to be connected to aging for quite a long time. This is a quote I often use in my general talks on glasses. You can see a piece of Roman glass, and in fact, the technology of glass comes with the Middle Easterners. And was popular in Rome. And St. Augustine, the older of you can probably still read this in Latin, but he actually already made the analogy between glass and people when he said, as we translate, "Are we not frailer than if we were of glass? For even if glass is fragile, yet if cared for, it lasts a long time. And you find grandsons and great-grandsons drinking out of the cups of their grandfathers and great-grandfathers." So here's Augustine on the question of aging and eternity. Thank you. I'll answer questions.
Any questions?
I can't hear them. How do I get them?
Can you hear me now?
How do I get questions?
Can you hear this,
Hello?
Peter? Can you hear?
Now I can hear, yeah, but probably just you. I don't think I
Okay,
can.
we have a handheld. I'll pass around for questions.
Okay, okay. Okay, we have a choice, okay.
Hi, Peter. It's Bob Laughlin.
Hi, Bob.
Well, not so cheery, Peter. I've been a troublemaker today. So,
You're always a troublemaker.
I know. Yeah, just okay. So, could you weigh in on whether the theory of glasses has anything at all to do with the lifetime of cars?
Can I talk about cars?
In other words, you're studying something that's thermodynamics, and you're comparing that with something that's pure economics and human engineering. Is there any relationship at all between them?
Yeah, I mean, yeah, this is always the problem. At the level of the economic level, I don't think I can say much because, of course, we don't really have theories of that really are mapping economic questions onto physics problems. Now on real cars, I think actually probably glasses have a lot to do with it because they have a lot to do with all those little plastic parts in there nowadays. Probably your old cars made out of metals were fine, but now your cars are all made out of plastic little gizmos. And those probably slowly change, and you probably won't be able to keep those cars running 100 years in the future. That's what I meant, that the engineering aspect of glasses is relevant to these kind of things. These time scales are much longer than things that we normally want to worry about. Reason why you like to use metals or glasses made of ceramics and things like that is basically their activation energies are much higher than stuff made out of plastics. Plastics is much easier to work with. That's why they would love to manufacture things out of plastics, and it's lighter. But in general, that also makes them decay faster. But it's very slow still.
Okay, good, thanks. Ciao.
You're breaking up. Okay.
Okay.
Could be.
Why need the mic? Hi, Peter, it's Herbie. I should ask you this when I see you, but it's easier now. So, I mean, glasses at the end of the day, of course, are a closed system. At least the,
Or what system? I couldn't hear you.
Our closed thermodynamic system. They're being driven by there's no external sources of energy.
Right.
As opposed to, as you know better than everybody else, cytoskeletal glass or tissue level ideas of glass have to face the fact that obviously there are external sources of energy. Is there in the offing some analogous phenomena, theory, whatever, for active glasses that?
I mean, the zeroth order answer is yes, although we haven't, it was actually what Apiwat was supposed to move on to work on before he got his job back in Thailand. We've talked about the cytoskeleton using Glassy ideas, and there's then this notion of an effective temperature. But that's a temperature caused by the motors, not the temperature that I was talking about here, this fictive temperature that sets the kind of structure that you're frozen into. That depends on how active the motors are. And I think that basically, I think it's likely that one could describe, until you get actual flows of glasses, that you could, flows of cytoskeletons, you can describe their just plain relaxation using that effective temperature, which is very high, by the way. It's about 10,000 degrees Kelvin, which you can measure by looking at the comparison of the fluctuation of the particle motion and how hard it is to pull on them. That's what gives the number 10,000 degrees Kelvin. That would describe the glassy characteristics of the cytoskeleton, but we've never really looked at that, really quantitatively quantitatively yet. One of the things that makes the cytoskeleton more tricky than the theory that I was describing is that the thing that made those very, very simple formulas work out was that there's many, many orders of magnitude between the microscopic time scale and the macroscopic time scale. 1 hour is, you know, whatever, 10 to the 16th or something, picoseconds. For colloids, the time constant ratio is more like a 10 to the 5th. And so you can't use just the asymptotic formulas the way we did for that. So that's why it's a project. Great.